So, Dr. Tukur, can we start? Am I audible? Please let me know. Yes, yes, please. Just a second. Okay. So, is my screen visible to all of you? Okay. So, dear students, welcome to the day 12 of your digital hardware design using VHDL course for 40 hours. In the last lecture, if you remember that we were discussing about the registers basically. Okay. And what we have concluded in the last lecture that a register is nothing but it is a storage device which can store data which is more than bit. And the fundamental block that is which registers is made up of is the flip flop, because a flip flop is can store 1 bit, and it is a 1 bit storage device. And when several flip flops are joined together, then it will become a register. Means if you will join 4 flip-flops, then it will become a 4-bit register. If you join 8 flip-flops, then it will become a 8-bit register. And similarly, others. Then we were discussing about the types of registers. And in types of registers, we came across serial in serial out register, serial in parallel out register, parallel in serial out register, and parallel in parallel out register also. Okay, these are the 4 registers which are being generally uh, taught in digital electronic course. है ना? Apart from that, I told you that we are discussing try register also and universal shift register also. Okay. So in last lecture, we have completed serial in serial out register. This one I have told you about the working and also its internal architecture, how flip-flops are connected together in order to create a register of 4-bit. We have connected 4 flip-flops in such a manner that it will become a 4-bit register. Okay, we have verified it using the designing for structural style of modeling. We have designed this using structural style of modeling and then verified it, does the functional verification, check the internal architecture as well as the simulation part. Similarly, we have also created the same using the IP modeling approach and also does the verification for that. So, similarly, I told you that you should try by yourself the serial in parallel out register and parallel in serial out registers. Okay, and these were the architectures that you can follow. I have taken these screenshots from the internet itself. It is available on the internet. So you try to make or solve these type of registers. Today I will be focusing on this parallel in parallel out register. Okay, because this parallel out register is very important because in most of the microprocessors internal architecture, the data would flow in parallel from one bus to another from one bus to another bus and from one register to another register. Okay, so this register is again very important from the point of view of understanding the microprocessor architecture. and how data flows. Okay. So in parallel register, you can see over here, if you follow this, okay, you can see I have taken four flip-flops, right? But in this case, you can see we can insert parallel data, the data parallelly. It is not like that the output of one flip-flop is connected to the input of another. Every flip-flop is having an independent input and independent output. Okay, these inputs and outputs are not connected to each other, or no common connection would be there. The one thing that is common, that is the clock signal. These all are synchronized with the clock signal only. Okay, so if I would like to draw the same table as I draw in this case, in the case of serial in, serial out, so how it works, let's see. Okay, I'm assuming that I'm assuming that there is one reset signal also, which I am connected. Let's say, let's say I have connected one reset signal, okay, which are common to this. Okay, let me make this reset signal, a separate reset signal. Uh, where should I make? Let me make it over here. This is fine. Okay, okay. Let me see. This is the reset signal. Okay, which I am inserting to all the flip flops, just like the clock. Okay, just like the clock. I want to insert the signal just like the clock. Okay, you can make the signal active low or active high depending upon your requirement. Okay, presently I am making it as active high, but if you want, you can make this signal as active low also. Okay, in some of the books you've seen that this signal has been made active low, or shown as an active low. So let us assume that this is a reset signal, just like the clock signal. Okay, and it is also made common. I'm inserting this reset signal from my side. Okay, just like this clock signal, this is having a reset signal. So now let us check how it works, as I will follow this table only. So first of all, whenever you will, after designing, when you will want to verify this, how do you verify? So in order to verify, what you need to do, first of all, you will put a reset signal equal to 1. Okay, when you put a reset signal equal to 1, then I am assuming all the outputs Q0, Q1, Q2, Q3, let's say, or Q1, Q2, Q3, Q4, as you wish, whatever the name you want to give, all becomes all becomes reset, all becomes 0. Reset means all becomes 0, right? All becomes 0. Now, after that, you will made reset equal to 0. Okay, because I am writing else if. Else if means If reset equal to 0 and there is a positive transition on the clock, because clock is also a positive as triggered, and there is a positive transition on the clock from 0 to 1, right? Then what would happen? Then whatever the value available at the input of these D flip-flop, it is available at the output in the first clock edge cycle itself. Let's say if I am applying D equal to, let's say that I am representing D as D0, D1, D2, D3, yeah, D1, D2, D3, D4. Let's say it is having a value 1, 0, 1, 0. Then on the positive edge itself, whatever the value that is written over here, 1, 0, 1, 0, it is available at the output in the first clock cycle itself. Okay, so this is the simple working of the parallel in, parallel out register. It's a very simple working of parallel in, parallel out register. Means you will get the data, whole data in one clock cycle only, right? So this type of concept is required in data forwarding inside the microprocessor architecture from one bus to another bus, and where we want data to be available in one clock cycle only and transferred in one clock cycle only. So let me create a new slide and let us try to design this, okay, using structural style of modeling. Okay, so let me take this VHDL code for, or let me copy this only, this whole slide, Control C, and let me put over here. I'm changing VHDL code for parallel in, parallel out register. Okay, using structural style of model. So what we need to do in this, in order to design this using the concept of structural style of modeling, what what basically steps that I need to follow? What steps does generally I follow? First of all, I identify the number of modules, total number of modules available in the architecture. So this is the architecture, and I am identifying the number of modules. Number of modules are 1, 2, 3, 4. Second step, identify and write the code for those module only ones which are having similar nature. So you can see there are four modules, but all these four modules are actually D flip-flops. And these D flip-flops are having the same inputs, same outputs. All are getting the clock or are getting the reset signal. So every flip-flop is having similar functionality. They are acting as a D flip-flop and similar nature. Means they are having equal number of inputs and equal number of outputs. So for that case, we will design this D flip-flop only once, and then with the help of structural style of modeling, we'll connect or recall this as a component in the main program and made connection four times. Okay, just we did in the case of SISO register, serial in, serial out. Same methodology we will follow over here also. So we already know that this is the code for D flip-flop. We already written this code last time also. Use IEEE.std underscore logic underscore 1164 dot all. Then entity D flip-flop. We have taken we have taken three inputs: D, clock, reset, input type, and Q, out, std underscore logic type. But here, what we do basically, instead of uh, making it as simple std underscore logic, make this d input, okay, this d input as std underscore logic underscore vector 3 down to 0. Okay, this we need to make is std underscore logic because these are of single bit. Similarly, will q will also be of 4 bit. Q out std underscore logic underscore vector 3 down to 6. Why we have done this? Because we know now these inputs are independent, parallel. So we need to apply the input at every D flip-flop. So for that, what I have done, I have created a vector D of 4 bits and given the name 0, 1, 2, 3, something like that. Okay. So that you can apply input at the same instant of time. Similarly, outputs also are independent. So I have created a vector Q of 4 bit. Okay. And so that you will get the output at the same instance of time after the valid clock signal. Okay. So now we need to write the code. So for writing the code, what we need to do, as I told you, if reset equal to 1, then your output should be resetted. So there are output is of 4 bit, so all the outputs will get 0, 0, 0, 0. Okay. So over here you will get 0, 0, 0 and 0. Else if clock equal to 1 and clock tick event, what we need? We need Q gets the value of D because Q is also a 4 bit and D is also a 4 bit. So we can write like this also because Q and D are of same size. Okay. And if else if neither clock is taking event or reset is 0, in that case you need to not to do nothing, just put else null. For one if you need to put AND, then AND process and AND architecture. Okay. So here we have created a program for D flip-flop and I will be using this D flip-flop in the main program. This is our main program over here. Okay, let me write over here. This is the main program. This is the main program. Okay, Dr. Tukur, can you mute? Somebody have unmuted. So this is our main program. Okay, here I will write entity PIPO is okay. Sorry, because I have created this for a single flip-flop. I need to write it in a I need to write it simple std underscore logic only because I am creating this for single flip-flop, not all flip-flop. Okay, so please make it correct. Similarly, this would be only single output. Okay, later on I will map it for four times, है ना, in the main program. So please make corrections. This need to be corrected. Okay. Okay. Right. So this is the program for a simple D flip flop where there is a single output, single input, and single output, not 4-bit. Here we need to create basically here we need to map. You can say all the inputs together. Okay. So for that, I need to define first of all entity. Let's say I will write in D in, and this D in now we need to create as 4-bit. D in I need to create a 4-bit. 3 down to 0. Okay. Similarly, your Q output Q I also need to make it as a 4-bit because this is so I need to define the entity of the main architecture, right? Okay. After that, architecture, just write people underscore arc and then people, parallel in parallel entity. Then call this D flip flop component as I told you. Just copy this as it is and paste it and replace entity keyword with the name component and over here write entity component here. If there is a required signal, then only you can put, otherwise you can remove. But in this program, I didn't find the use of any signals, right? So I will be removing them. Okay. First of all, I will be now once I have created the component, I have to call it 4 times. Okay, for as per the architecture. Let for DFF1, DFF2, DFF3, and DFF4. Okay, so let me call it for first of all for DFF1. This is DFF2. Let's say this is DFF3, and this is DFF4. Right? And what I need to define first of all, I need to define the file name which I have created over here. Then I have to write port map, and then in sequence I have to write first of all inputs and outputs. Just I have defined similarly as in the case of D flip flop. D clock reset Q. So I need to map this D flip flop component with the main architecture inputs, entity inputs with this. So what should I write? I should write, let's say, D in 0. D in 0. Let's say this is 0, this is 1, this is 2, this is 3. So this is D in 0. Okay, clock reset, and this is Q out 0. Okay, similarly for D flip flop, what should I write? D in 1 and Q out 1. Clock and reset are same. Similarly, for third flip flop, D in 2, Q out 2. Okay. Similarly, for fourth flip flop, I should write D in 3, clock reset, and Q out, and P4 underscore R. Okay. So this we have completed the code for parallel in, parallel out register. Very simple. Okay. If you want, you can verify this also using the software by making the program in the software. So let me try and check whether it would work or not. Okay. Just take a 2 minutes break. Meanwhile, it is opening. So let's create a project. Creating a new project in Vivado. First of all, I will be creating a project for which PIPO 4-bit. Okay. Next, next, let me create a file. The file is of type VHDL, just we did before also, and write the name DFF. Same name as we have seen in the PPT. The same name we have to specify, right? Okay, then next, choose board over here. Which board? ZYNQ. Next, and finish. It will create a project for you. Okay, so for D flip-flop, let's write the architecture name because the same name is there. You can see over here in the PPT. If you will see, the name is DFF underscore R. Okay, and we need to define only the inputs. First of all, we'll need to define the inputs. D clock, then reset, then output is Q. This is out. Okay, and the entity and the program is created for us. Just we need to define the now architecture, right? So we can copy this that architecture directly from the program itself. I will copy the architecture from here only. Copy, copy, and paste. Right? If there would be any error, it will show you just like it is showing over here that you have not put the semicolon by red line. Okay. So this is the D flip-flop program. If you want to test that, you can test it. Otherwise, you can use this program as a component. And for that, you need to create one more file from here itself, which is a main file, right? Main file name is people. Okay. Then finish. Architecture name is, and here we need to define the inputs and outputs. What we have defined over there. The name is D in. It is an input. How much? 3 down to 0. Similarly, clock, reset, output is out. Again, it is of 3 down to. Okay. So you can see we have created this file, people, over here. And now I'm going to write the main program. So for write into the main program, I will copy the code same which I have created for main program. Okay, from here itself, let me write. Okay, begin, and then this one also. Okay, you can see over here it is showing some error. This we need to create, sorry, with this we need to write as out. It is showing this error. Okay, now all errors are removed because we mistakenly written this queue out as input type. That's why it is showing you errors. Now this program is okay. You can control S. As you can see, you will put control S automatically. This main program, people, will become your main part, and all these components, D flip flop, will become the sub part of these main program. Automatically, these files are assigned. Means you have called D flip flop component four times. One, two, three, four. For four flip flops that are connected in the form of the architecture. Now you need to simulate, run, check this file only. This is the main program. This is the main architecture. This is the benefit of structural style of modeling. Okay, right. So what you can do, you can check, simulate this. You can check the output on the simulation. Further, you can also check the architecture schematic, that how it looks. Okay, so let me check this schematic. It is showing some error. We will see later on what error are it showing. So you can see over here, this is the diagram of this parallel in parallel out register. You have four inputs. D in, you have four outputs. Q out. Every flip flop is getting clocked, and every flip flop is getting this reset. Okay. Further, if we want, we can run simulation. Okay, you can see over here, right? This is our inputs, four inputs, clock, reset, and out. Okay. Let me zoom out this. So what I will do, we'll apply the required inputs and check whether it is working as per our requirement or not. Yeah, or as per our defined functionality or not. So at inputs, this is a 4-bit input. I need to specify some value. So for that, just right click and force constant. You can put a binary value. Let's say 1010. Okay. Then we'll start with reset equal to 1. Okay. I will start with reset equal to 1. So force constant, binary, reset equal to 1. Similarly, let's apply a clock signal. Similarly, over here we will put a force constant. First of all, we'll make this clock signal 0. Okay. Now I will run this for a specified time. Okay, I will run this for a specified time. Uh, it is hiding behind this. Okay, now it's fine. Okay, okay. So let me run this. What would be the expected output when we have applied reset equal to 1 and when we have applied input at this? So our output should be expected to be 000 or resetted irrespective of whatever the value of the clock or whatever the value at the input, because reset is having the highest priority in our case. We have designed this pell in pell out register in such a manner that when we apply reset, whatever the input is there or whatever the clock signal is there, it is ignored and the output will be reset. Okay. So although we have applied some input over here, but your output will be resetted as we apply reset signal. Okay. Just check it out whether it is happening or not by running. Okay. So you can see over here, you can check. You can check when you have applied input 100 1010, you have applied clock equal to 0, but it hardly matters because reset equal to 1, then your output is 0. Your output is 0. Okay, change the radix of this also to binary. Your output is 000 as expected, as per our requirement. Now, what we will make reset equal to 1, reset equal to 0, will force constant and make reset equal to 0. Okay, and now I will apply a valid clock signal from 0 to 1, which is a valid transition. So I will be changing the clock signal value. Previously it was 0, now I am putting 1. So there is a valid change, going to be a valid change in the clock signal 0 to 1. And when it happens and reset is 0, whatever the value that is available in the input, it should be available at the output in the single clock pulse cycle. That is our objective of this PIPO register. Right? Let us check it whether it is happening or not. You can see as I applied a valid clock signal means there is a transition from 0 to 1. As there is a transition from 0 to 1, whatever the value that is available at the input, it is available at the output in a single clock cycle. Okay. Similarly, when you apply a new input over here and then again change the clock signal, a new value you will get the output. Okay. This way, what you can do, you can check your system, right? You can check your outputs or simulation. Let me take a screenshot of it for you people. Let me save it so that you will remember that we have done the simulation of it. Okay. This is more than enough. You can copy this and you can paste it over here. Okay, right? You can paste it over here. So it would give you an idea that okay, we have done the functional verification also, like you have did in the case of CISO. Over here, you can also done the same thing, functional verification. Same thing. You can put it over here. That is functional verification. Right? Okay. Okay. I hope it is clear to everybody. Now, if you want to save that uh, schematic also, you can take the screenshot of that schematic also. Okay, this is the schematic. Okay, if you want to take the screenshot, you can take the screenshot of that also. Okay, let me take for you. If you want to rotate it, you can rotate it also like this. Okay, if you want okay like this, you can do that. Hope it is clear, dear students. So what we have done today, we have successfully tested the parallel in parallel out register. This is a very important register because uh, this is a very important role inside the microprocessor architecture in order to transfer the data from one place to another place on a single clock cycle. Right? I have created this design using a structural style of modeling approach. Even you can create this in a very simple manner also. Okay, if you want, you can write this code in a very simple manner also. Okay, I have chosen the structural style of modeling just for the sake of understanding that how can you create bigger circuits. Okay, and follow the similar approach for the designing that I have did for the CISO. But if you want, you can design this parallel in parallel out register in a very simple manner using behavioral style of modeling also. Let me show you what I'm trying to focus or what I'm trying to say to you. Okay, if you want, you can design P and PO using simple behavioral style of modeling also or data flow style of modeling also. Okay, how? Let's see. Very simple. It is very simple. Let me show you. I have copied the same program. What I did in this, let's see. I will put entity over here people, right? Similarly, people. Let me create this D in std underscore logic underscore vector 3 down to 0. Similarly, this Q also, it would be it would be a 4-bit also, right? And in a very simple manner, I can write the code for it. Okay. D clock reset, similar concept. If reset equal to 1, output is 0, 0, 0. Else if clock equal to 1 and clock tick event, output will follow the input. Else null, and if, and process, and peepo underscore r. Okay. So what it is representing, that again the same thing what we have created over there. It is representing the same thing, but in a simple manner. You have created a register. Okay. You have created a register, simple register. Okay, which may be, let's say, uh, which you can divide it into 4 parts just to understand the process. Let me draw this so that you can understand. This is one part. Second part, it is the same thing but we have designed over there. That was at the architecture level, and that is simply at the algorithmic level. Okay, it is having what it is having input, it is having output. Okay, all, and these inputs and our outputs are of how much bits? 4 bits. This is also of 4 bits, and this is also of 4. This is just a representation to understand the process. Okay, and this is also a 4 bit. This is also a 4 bit, right? And there is a clock signal, and there is also a what? There is also a reset signal, right? There is also a reset. There is a clock signal also, and there is a reset. Let me write clock and reset. Whenever you will apply a valid clock signal, the valid clock signal would be positive as triggered signal. है ना? This is your valid clock signal. Whenever you will apply a call and you will put any value over here, it will be available at the out. And what are these? These blocks. These are blocks are nothing. These blocks are, this is D in, of all the flip-flops which are joined together in the form of bus, that is D0, D1, D2, D3. Similarly, this is Q out of all the flip-flops which are joined together and acting as a, okay. So you can see over here we have a multiple approaches of designing of the same thing. This is the simplest approach where you can design a parallel in parallel out register. Okay. Sometimes this register is also termed as a bi register. I have also uh, told you previously. Sometimes this register is also told as bi register. Bi register. Okay. Sometimes this is register is also told as bi register. Okay. Whatever the value in this case, when you will apply a clock signal, valid clock signal, make reset 0. Whatever the input you will apply, suppose 1010, and as this valid clock signal comes, this input value is available at the out. And these blocks are representing the flip-flop. This is flip-flop 1, flip-flop 2, flip-flop 3, flip-flop 4. Okay. Because every block is storing one bit of data. So I have cleared to all of you. Please let me know if you have any doubt. Please ask. Just taking a 2 minutes break. So I hope there is not any doubt because I have not seen any message in the chat. So I am assuming that everything is clear to everybody. Still, if you feel, then you can put a message on the chat so that I can respond to you accordingly. Now, following the same process, let me give you an example of one more register, which is a very important, again, from the point of view of a microprocessor architecture. Okay, referred as a try register. Okay, so let's see the designing of a try register using behavioral style of model. Okay, using same behavioral style of model. For understanding this tri-state register, your try register, uh, let us understand the concept first. Okay, how it works and what is the concept. In a try register, it is similar to bi register, but the difference is that it is not having a reset signal alone. It is having two signals. Okay, one is called write signal and another is called read signal. Okay, let's say let's say one is called write signal and another is called read signal. Okay, you can make them active high or active low depending upon your requirement. For an example, let me make it active low also. That is, it is also active low, it is also active write bar or read bar. In that case, the signal will have some negative edge, negative label trigger. Okay, it is having negative label trigger. Okay, so this means it is activated at logic 0, not at logic 1. And what is the working of this try register? Let us understand how it works. In this case, it works on the concept that if there is no reset signal, that if clock equal to 1 and clock tick event, and in that case, if your write signal is activated, है ना? Write is write means this write bar. Okay, if this is activated means it is activated at 0. Then, है ना? If this write bar is activated and read bar is deactivated, because both signals cannot be high at the same instance of time, and read bar is deactivated. Either you can write or either you can read. Then in that case, what would happen? Your input, there would be an intermediate input, let's say there would be an intermediate input U, and that U is represented by these four blocks: U0, U1, U2, U3. It is it stores that value basically. Means the value which is available over here, that is stored inside this U. Means U gets the value of D in. Okay, and else else if else if else if your write is deactivated, let's say 1, and read is activated because these are active low signals, then in that case, whatever the value stored in U, that would be available at the out. Okay, else null, else nothing. So this is the logic. What I'm trying to say to you, that it is a type of register which does not allow the input, it does not allow the input to be available at the output instantly. Rather, it will store it intermediately somewhere, and whenever proper read signal is applied, then only that stored signal will be available at the output. It is similar to like some tri-state buffer. इसलिए that's why name is tri-register basically. It is similar to like some tri-state buffer because in that case also these tri-state buffers are put at the output side. Okay, and whenever this input is available and you will apply a valid clock signal, then whatever the value that is available at the input, it is available, not instantly available at the output. Rather, it is stored previously somewhere, okay, before the tri-state buffer. And when you will activate these signals, that value will be available at the output. So what it does, it will save the output device. Suppose you have connected some output device over here, and that output device is connected to the in that output device is input is connected to the bus of this register. So that value, when you apply over here, it is not instantly available at the output, so that it cannot change the this output device. Okay, rather, just a second. Hello, Dr. Tukur. Again, the meeting was ended disruptly automatically. So I'm again sharing my screen. Please accept my request. Okay. Students are joining. If you want, you can record it again. Okay. So, dear students, let's start again. Meeting was disrupted automatically. So, mm, it is again ended. So dear participants, uh, there was some problems going on, but let's start again and try to use this. So let's see again from start from here. So what we have concluded that tri-state registers are very useful where we need not see that the input or the output you can say is available to any other device instantly. Okay. So some input is there, some is there, and it is basically you want to send that input to the output device, but not at the instantly, right? So there where this basically tri-state register comes into picture, and again a very important register in the microprocessor architecture where you want that tri-stated outputs, okay, or you do not want that the inputs should not be available at the output of the other device input at the same instance of time, okay. So it will be delayed by one clock cycle, and it depends upon the read bar signal when you will apply read bar. So let us write the code for it. How do you write the code for it? So in case of reset, let's say write bar and read bar. Let's say I'm writing this, and over here also, let me write in place of reset. Let me write write bar and read bar. Okay. So in this case, I need to change some of the statics like this. That if clock equal to 1 and clock tick event, then if write bar equal to 0 and read bar equal to 1, means read bar is deactivated and write bar is activated because both are active loop. Then in that case, let's say create a variable over here, u variable, std underscore logic underscore vector type, same size, 3 down to. So when this happens, that's u variable will get the value of d in. Okay. Else if else if write bar is deactivated and read bar is activated, so whatever the value that you have written, that should be transferred to the out. Let's say I'm writing q, or you can write q out also. And if it is a variable, then I should write colon equals to, because this is a variable assignment operator we have discussed in previous classes, and it is a signal, so the u should be transferred at the out. And if both these things are not correct, means either both are 0 or both are 1, nothing. Okay, nothing should happen. Else null, right? And if similarly, if clock equal to 0 and not getting any event, then in that case also, for this if, you will put a else null, and process and up. Okay, so this is the code for the try register. You can verify this code also in your Vivado software and check it out, it's working, whether it is working perfectly or not. Okay, right? Last we have left with now universal shift register. Universal shift register. This is very also a important register. Okay, and generally we have been teased in digital electronics about this universal shift register. What is this shift register works basically? It can perform multiple operations. Means it can shift right, it can also shift left, it can also work as parallel in, parallel out, and it can also put work as by register. No change. Okay, means no change means whatever you have applied at the input, it is available at the output. Nothing has been changed. The previous value, what is the previous value is there? It is the same as the next value. Okay, so this is the architecture of this universal shift register. You can see over here. And suppose if you are making a 4-bit register, then there would be a requirement of 4 flip-flops which are connected to clock and reset signal, or you can say clear signal over here. Okay, and you can see one thing, that the output of one flip-flop would be the input of second, but through a multiplexer. Similarly, the output of this would be the input of third, fourth, fifth. Similarly for this direction as well as for this direction. Okay, for serial in, there is a one signal 1 where you will apply input. Similarly for left stream, you can apply the input at 2. 0 stands for no change. 3 stands for parallel in, parallel out. Whatever you will apply parallel in, you will get the parallel out. Okay. And the select line of the multiplexer, these are S1 and S0 are the select line of the multiplexer which are common to all the multiplexers. So whenever you will apply 0, 0, whenever you will apply 0, 0 over here, 0 is selected of all the multiplexers. And at 0, what is there? What is there? At 0, you can see at 0 output is connected. This output is connected to every, you can see. And the output is connected to this 0. Means whatever there is an output, the same will pass through these D flip-flops and again available at the output. So no change. Because when you will apply 0, 0, this 0 input is selected of the multiplexer. Whatever it is, whatever the value available at the input of this, it has been passed through this and available at the clock, D flip-flop input. When you will apply the clock, it is available at the output. Okay. So when you are applying 0, 0, nothing is changed. In case of 0, 1 means shift right. In case of 0, 1, when you are applying 0, 1, you are inserting some data from here 1 into the first flip-flop or first multiplexer. Okay, it is available at the output of first flip-flop when you will apply a valid clock signal from here. This output of first flip-flop is connected to the input of the input 1 of the second multiplexer and then to second flip-flop. So in this case, this bit is available at this point. The value available at this point will be available at this point. The value available at this point will be available at this point and so on. So it seems like that you are shifting the data into the right order. The similar thing is for left string. When you will apply 1, 0, you will apply data at 2. Okay. It is available at D flip-flop. Some value is there already. Previous value. It is available at the second multiplexer input and it is available at the input of second flip-flop. Similarly like this, and like this. When you have 1, 1, there is nothing parallel input. Whatever the value you will apply at B1, B2, B3, all these inputs, it is available at the output directly. So this is the example of universal shift register. What I will suggest you please try this universal shift cluster designing by yourself. Okay, as an self assignment. Let me hint you what you need to do. If you are going to design this universal shift register using structural style of modeling, then first of all you need to identify the components, number of components. So in this you can see there are various number of modules, 1, 2, 3, 4. Suppose you are making a 4-bit register, so 1, 2, 3, 4. Similarly 1, 2, 3, 4. So there would be around 8 modules in all. But you can see that out of these 8 modules, 2 modules are like that they are having the similar nature and similar number of inputs and outputs, because this one module of 4:1 multiplexer is having 2 inputs, 4 inputs and 1 output. Similarly, this D flip-flop is also having the similar nature, but this 4:1 multiplexer is repeated 4 times. Similarly, the D flip-flop is repeated 4 times. So what you will do? You will write a code for 4:1 multiplexer using behavioral style of modeling. Then you will write a code for D flip-flop using behavioral style of modeling. Then write the main program, components in the main program, both these components in between the architecture and begin. And after that, with the help of port map, please try to connect the inputs and outputs as per this architecture. And then verify whether it is fulfilling your requirement or not. Okay, so this is a self assignment for you. You people try to write the code by yourself and test. It is a very small project. Okay, it can be you can design this as a minor project. Okay, and do this functional verification and simulation. Okay, very good to understand. So understood, students, right? So with this, okay, if you have any doubt in any of the topic that we have discussed, right? So please tell me, and whatever uh, whatever the self assignment I am providing you, you please try to do yourself. Okay, one, two, and three. This we have done. This we have completed. Okay, this I have covered in the course, and this I want you to do by yourself. Okay, and try to submit with your mentor as soon as possible, because already there are lots of assignments, because there are 12 lectures completed, and you can see over here that I have given you time to time some assignments during the to submit all that self-assessment assignments to your mentor so that we can check them and evaluate you. Accordingly, you will be graded. Okay, and those who will not submit, they will not be graded. Right?